Here is the uncertainty relation, the product of the range of a coordinate and the range of the momentum. In other words, we're going to see a classical uncertainty relation. This is Heisenberg's idea, comes much later than Planck's. Okay, but it's just a bunch of balls bouncing. Okay, well, it's not a bunch, it's one getting crunched, as I call it, the name for it is obscene, really. This is abuse. This is terrible abuse. This poor little ball here is going to be crushed by something that's infinitely massive. Okay, so here it is standing still. Here's the trajectory of the ball. Okay, minus radii of each of them, so we could actually see where the center of each one is on the time graph. Time now is down, okay? And you know this has a velocity 1, that's a unit slope right there, okay? This has velocity 0, but it's going to pick up how much? How much does it pick up? And don't listen to Paul Hewitt, but listen to our little graph for the case of infinite slope over here, where we picked up 2v1, right? v1's 1, so it's going to pick up 2 after a collision, right? So this thing's coming through here with a slope of 2 to 1 in space and time, okay? Then it bounces off on this side an infinitely massive wall, lots of infinitely big things here, and comes back with -2. Then it runs into this guy that's now reduced to space here from delta x equal that to delta x equal to that, and immediately whacks it another 2. So it goes to 4. Okay? And then it doesn't take it very long to run into the wall and come back. Okay? With a -4. And then another 2, so it goes to 6. Comes back with a -6. Gets another 2, 8. Comes back with a -8. And so on. 10, 12, 14. It's an implosion. That's abuse. Can't do much worse than that. We're crunching this thing. Okay? But the idea is that no matter what scale I look at, I'd see a diagram something like that. So if you extend the lines of this, and I'm going to ask you to go ahead and construct this thing in some detail, you find that all of the trajectories on either going this way or that way, the ones that are going that way, all intersect down here at 3 units from there. Remember the 3 that came out of infinite mass ratio there. And the other one, the come back trajectories, they all intersect right here. So this monster mash, as I call it, does that. Now, the connection of this to uncertainty is just as I cut down the range of the coordinates that it has, the momentum goes up and the range of momentum goes up, so that roughly speaking, delta x, delta p is some, well, maybe huge number times the Planck's constant. In other words, this is really what Heisenberg's principle looks like when you're looking at a classical object where the quantum numbers would be astronomical. And it's good there too, it has to be. It isn't just good when the ends are onesies and twosies. So that's kind of neat to actually, have that. So what you see is a decreasing space, increasing speed. As I decrease the speed gets bigger. Delta p gets bigger and proportional to how delta x is getting smaller, all the way, in this case, to absolute oblivion, crunch, right at that point. Okay? Now, the animation of something like that is not too telling, but let's just run it anyway for the sake of argument here. Let me go ahead and return to the lecture on this screen here, go forward to the point where we can actually animate the portal crunch. And this is just a, just so you have a quick movie picture. There we go, okay? Bang, 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 okay? And the simulation is good enough that it can actually return you and make it do it again, but by that time the time is over, so you won't see the time graph of that, but there is the monster mash for what it's worth, okay? This graph here is probably more telling, and that is that the area, the phase space area, x versus p, well, velocity versus coordinate, is constant. Okay? All right. There's the kind of the picture that we had. And this one right here, I think we'll just do the same as what we've seen there. So this is the velocity plot being shown there. So this is the kind of graph that I'd like you to make, but I'll give you a particular velocity that isn't zero, see if it works for that, and how much it works. And then also notice that when you do some geometry of it, and this is all in the textbook, when you do some geometry of it, you discover that if you just extend those things and then draw another set of boundaries, you could have that going on in here, and it would be exactly a mapping of what's going on here. And then you can balance the whole thing so that it's the same on both sides. And then you get a diagram that's like this. And so if we have 15 more minutes or so, I'd like to play a few, I'd say a few things about what's going on here. This is what I call the tiny Big Bang. And I'll explain what I mean there. I mean that I have a one-dimensional universe, well, two if you count the phase space, and let's go here. So this is the name, a wave analogy, tiny Big Bang. Okay, and here we start with a wave function on the simplest quantum mechanical problem there is, the one that you get in a sophomore physics course, and it would simply be a particle on a loop, on a ring. Okay, no potential, nothing, it's just kinetics. Okay? And what I do is I make a wave function that's a Gaussian, or some other function that's narrow, could be a Lorentzian, but Gaussian is much nicer because it goes off e to the minus x squared, so it really has very little probability any distance from the thing. So if I make a Gaussian that's that big, there's virtually nothing anywhere else. So what we're going to see is a wave that starts completely at one point, that is completely at a point on the other side of this cylinder. This thing right here needs to be wrapped and glued together on the other side. So what we're looking at right here is in the front, and we're going to start a Gaussian in the back that's really small, okay, really tight, has a really small delta x. And you know what that means. If you have a really small delta x, you've got to have a really big delta p, because the product's going to be a constant, right? So basically, when you make a small delta x, you're making a bomb. Bang, right? It's just full of all velocities. It just wants to get the heck out of there, right? But in a beautifully coherent way. So coherent that eventually it reforms. Actually, it reforms on this side and then forms on the back. This is the Bohr orbit, simple Bohr orbit. No radial apart, just angular, just this. Wave function on a circle. Okay? Can't get any simpler than that. All right? Has a quadratic spectrum, and that's what makes all of this happen. Okay? So that's what I'd like to show you. And this is just a picture here of what we'll start off with. We'll start off with a Gaussian wave that is at the North Pole, and there it is. This is this thing unraveled to that size. Okay? So what I will be doing is I will be clicking just the set t equals 0 on this, but I have to actually get it up on the screen here. Maybe I go ahead and leave this one to show still lifes.
Use the
and
far
I'll go
one.
on this one. Pardon?
Use the far unit because it's much quicker. And you
Okay.
recall the carpet lays out real
Okay.
slow.
That's fair enough. Let's get this one shut down here.
Do them both. But
I don't know how far it's got. I think it's gotten all the way to Fort Smith by now. Let's just pause this guy, and then I'll return. And I've got to use this one right here. Tab.
quick.
There we are. And I will go forward on this one until we get to the tiny Big Bang. Okay. So here we go. Let's just try this one. See if it's fast. I'm not sure it is, but it won't make any difference. It's better to see it sometimes slow. That wasn't what we wanted. That is definitely not the particular wave simulation we're looking for here. See if
Quit.
something crazy is going on there.
Just quit.
Probably a bad choice because I haven't upgraded that one to local. Let's go ahead on this one right here and see if we can get it to do the wave simulation. No, that's weird. You might try playing with it because of, I think what is the scenario number probably is what we're getting. We're getting beginning fun on.
Apologize on that one.
Yeah.
I twitched it.
This thing is full of all sorts of wave programs. We're looking for, probably at the bottom there.
Yep, here it is. We'll do the boxcar first.
No.
With this, okay, Gaussian with distribution.
Yes.
Because we don't have the time.
There we go. Okay, get out of the way here. It just blew up and went around, started interfering with itself at the South Pole, and then is interfering everywhere. Now it's just a dance showing you different symmetries that it can produce. And we can produce all the way up to about 10 or 11 or 12-fold symmetry. Half of that. We can produce 5s to 6s to 7s. And you'll see that was a 7 there, I think. Anyway, all of the rational numbers that have denominators smaller than about 7 will have signature on this thing as it rings around its little universe. And this is the Gaussian distribution that makes for a really clear picture of the same sort of trajectories, but now trajectories of zeros as the monster mash. And there, it's all forming on the South Pole just briefly, and now it's just going to repeat and reform like that way up here if I let it go. But this is where it stops. Okay, just that. And that's fast enough to, get it where we've got the thing. Now, what is it that's going on here? There's a lot of really beautiful number theory. And I'd hope this would have something to do with quantum computing. So far, it's not turned out to be useful for that. I mean, basically, this is just stepping through it to show you what we've got. Okay, there's a typical 3/5. Whenever you have a fifth, 1/5, and then 2/5, and now it's 3/5, you get a little pentastar, okay? A fivefold symmetry, okay? All of the symmetries, you'll even be able to see, if you look really carefully at this moment, you would see 11. All of the odd numbers give you the symmetry that it says. The even numbers, you have to divide the denominator by 2, and then this is going to give you a 2-fold symmetry. This one's going to give you a 3-fold symmetry instead of a 6-fold, you see. This one with an odd number is going to give you the 3-fold sort of honestly. And you can see it there, 1, 2, and 3 peaks. Those are peaks. The white regions are zeros, or near zeros. Okay? So, real question is, and there's a typical 3-fold thing, see how close to 0 it is in between for that one. How does this work? And this is basically, you draw a bunch of lines just with integer slopes. That corresponds to quantization, okay, as far as velocity goes. And then what we're producing here, and this is very important for classical mechanics as well as for this wave mechanics, as you start to match things that are going back and forth in a two-dimensional phase space, you look for the things that are going this way, where they cross things that are going this way. This one has got a slope of 1 over d2, which is some integer, okay, I guess it would be about 8 or 9 or something right there. And then there's 2 of those, and then there's 3 of those, and there's 4. So this thing keeps wrapping around, runs into its point again, and then just keeps going. So this is just a straight line wound around that cylinder, right? With a slope d2, okay, whatever integer that is. And then there'll be others coming the other way, okay, in this particular one, let's say a d1, a slope, all right? Okay, well they run into each other and make all of that structure. That's really all it is, and that's all the monster mash is. But boy, it's kind of beautiful, and it has all kinds of really funny number theory in it, which I'd like you in the next 5 minutes to see for the first time, and we'll see it again later on. Okay, so the question is where, of many points, but let's just pick the module or something, where does this particular thing with slope d1 run into this thing with a slope d2? Okay, well it's right there, and then it's going to happen again other places, but that's what we want to do. We want to calculate that. Okay, well it's just an algebra, very simple algebra, using the slope equation. Okay, there it is. Okay, that's its equation in terms of phi, and the time is this way, okay? And so the idea of these two equations being equal gives us the coordinates of the crossings, and the crossings can either be places where zeros are or where unzeros or peaks are, where something is. But one of the things I learned from this was if you want to answer questions in quantum wave mechanics, you don't look where the peaks are. You look where it's not, where it's zero. The zeros are more robust and they have more sort of knowledge of what's going on. Okay, so it's not so much that you're here in this room, it's that you're not everywhere else. And we play that game very much here. Now this time, the time that this occurred, which is time is that axis, okay, is given by a very funny fraction. The fraction is called the Ferry sum, after John Ferry in 1815 was trying to figure out the resonances of the, I think, the Bay of Fundy, which has very high tides and all kinds of oscillations in between the big ones. Okay, and the idea he found was if he found something at 1/3 and he found something at 1/5, he would also find something at 1 plus 1 is the numerator, that's 2, and then 5 plus 3 is 8. 2 over 8, you find something at 1/4 if you looked very carefully. That would be the Ferry sum. It's also the sum if you're grading UP. That's where they had fractions in UP1 on the first few days, or weeks, or months, or maybe their whole life. Okay? But they don't discover what John Ferry discovered. Right? And then, on the other side is where is the angle, what is this actual place, the coordinate that comes in. Well, you solve the thing for that as well, and this is a cross product discovered by somebody named Ford in about 1938. It's a funny kind of cross product divided by the sum of the denominator slopes that are assigned to each of those green, and then another number, D1, assigned to the brown. Okay, so these are important numbers, and here is the way to analyze it. That's really cool, and we're making a big fuss about this, and this is in PHYS letters. I mean, what is it doing there? But my student Lee was very good at seeing some things about this. And the basic idea is, if you're going to play with fractions, why not plot the numerator versus the denominator? Okay? So to understand a fairy sum, say you're doing right here V0, 1, V0 is 0, 1. Okay, that's 0 over 1. The V1 here is 1 over 1, and this is 1/2 right here. Okay? A fairy sum is simply a vector addition of those two. V0 plus V1 gives you 1, 2. Okay? In other words, it gives you something that has a slope of 1 to 2. It points right at 1/2. So here's a real line up here, and here's a map where we're going to find all of the rationals with a denominator greater than whatever this graph is. Okay? And then it keeps going. It goes forever. You can get all the rational numbers mapped out by doing this funny sort of numerator versus denominator plot. Now, the unit circles, these two unit circles are the start of this thing. And what we're interested in is the vector V2 that comes from the fairy sum of these two fractions. It's 1/2. It's the vector sum of those two, as I said down here. And then what you do is you look at that and you draw a line from the center of this great big circle through the intersecting point of the fairy vector that points at 1/2, and you'll point at the center of the next circle that's tangent to those two circles. That's what's going to happen. It's pointing to the center of the next circle that goes with 1/2. Okay, that's the forward 1/2 circle right there. Now, how many people here have seen the movie Titanic? Anybody? Hands? Just about everybody. The connection between the movie and this mathematics it should be obvious. Is it?
Yeah.
Remember when the girl had that wonderful, brilliant sapphire diamond, and she posed in the nude for the artist? Now you should never forget this. That's an anthropomorphic connection that you can't wash. Okay? Anyway, it gets better. What if she had more jewels? Let's go for the next fairy sum. This plus this, 1/3. That's the next one. There it is. You do the same thing with these, and there's a magic circle that you get the center of virtually for nothing. And it just gets more and more complicated as you go through. Basically, all of the it's telling you the significance of each one of the resonances that make a pattern over there. These are the rationals that we kind of have well exposed with this particular wave here that has a range really of it's just 10, plus or minus 10, 11 or 12, depending on how you want to count things here. So anyway, I thought you should know about this. This is just something that's I find really beautiful, both physically and mathematically and cinematically. But the structure that goes inside that, these little rectangles here that are the fractions, they're all being drawn too. Every one of these things has in a rectangle has exactly the fraction that's represented here. So I should say, watch this space. Okay. All right. we have a minute or two, according to my ill-gotten watch here. Any questions, comments?
I have a question about so what do the circles mean? What's the significance of the circles?
Each one corresponds to a resonance, like the 2/5 or the 2. This guy right here, okay, is quite a bit more significant than 3/7 or any of the 7. There's 2/7. There's 1/7. So right away, what you're doing is classifying the circles according to how they fit between a circle and a line. And let's see if there's anything else I can mention. The size of those circles is the square of the, in other words, relative to this thing, that thing is 1/2. It's got a radius proportional to 1/4, and then this one 1/9, and this one 1/16, and so forth. So you square those to indicate how much of a fuss. Obviously 1/4 makes a big fuss here, but it doesn't appear very often. Here we're looking at 2/7, which would be exactly the same as 1/7 down there. And the 7s all have a 7, count them, 1, 2, 3, 4, 5, now something's happened. I missed 2 there somewhere, but basically 7 lumps of a certain height. So the circles are related to this guy. The 5ths correspond to something of a certain height. And basically we're just conserving probability. The area would be the measure of the probability, the integral of the curve. Good question. Anything else? Well, this is something else to play with. So far, we're trying to figure out what happens now when the wave expands in 2 dimensions. Now you're talking about angular momentum calculus, and we put that in that paper, and we're still puzzling that. There's all kinds of weird things going on there. Okay, well, we'll have a good Labor Day weekend. We'll see you on Wednesday next week.